3 million years ago, a small creature lived in the African savanna, completely covered in thick fur. It climbed trees, sought shade at midday, and never ventured into open ground during the hottest hours of the day. That was the smart move, because stepping into the open at noon meant death, brain overheating, heat stroke. Today, its descendants climb Everest, swim the English Channel, and sit in offices at 72 degrees Fahrenheit. All of this essentially hairless, without a single visible hair on most of their bodies. How did that happen? Among all mammals, and there are around 6,000 species of them, humans look deeply strange. Bald, sweating, with thin, vulnerable skin. By every outward measure, not the most protected creature on the planet. But that very nakedness turned out to be one of the greatest evolutionary advantages in the history of life on Earth. Not a weakness, a weapon. You are the only mammal on Earth that sweats through its entire body. That's not a metaphor. It's literally what separates you from every other creature alive. A chimpanzee, our closest living relative, has around 170,000 sweat glands across its entire body. A human has 2 to 4 million, 20 times more. But why? And why us, out of all 6,000 species of mammals? Why did we need to lose our fur and grow that many glands? The answer to that question changes how you understand yourself, and why humanity survived at all. Fur isn't just warmth, it's an air conditioner. Let's start with what fur actually is. Most people assume fur exists to keep animals warm. And that's true, but only partly. Fur works both ways. It traps warm air close to the body in winter, but it also traps hot air close to the body in summer. It's an insulating layer that, when built right, protects against both cold and overheating. Look at a camel. It has thick fur, and that fur shields it from the blazing desert sun, preventing outside heat from penetrating inward. For an animal that barely moves during the hottest part of the day, that works brilliantly. But here's the problem. Camels don't chase prey for 2 hours under the midday sun. Our ancestors did. 3 million years ago, something changed. The forests of Africa began to retreat. The climate was shifting, drier, fewer trees, more open ground. And Australopithecines, furry creatures standing less than 5 feet tall, began leaving the shade of the trees and venturing into the savanna. It was a disaster. At noon in the savanna, air temperature 104 degrees Fahrenheit, ground temperature 140 degrees Fahrenheit. The chimpanzee knows this. In the heat, a chimp hides. It doesn't hunt at noon, doesn't chase prey for hours, doesn't run after antelope across open ground in direct sunlight. Our ancestors started doing exactly that. With fur, that kills you. The internal body temperature of a human must not exceed around 108 degrees Fahrenheit. Above that, brain damage begins. Muscles during physical exertion generate enormous amounts of heat. Add the sun from above. Add the hot air around you. Add the insulating fur that won't let the heat escape. An animal with thick fur running for an hour across the savanna at noon dies of heat stroke. This was an evolutionary dead end. Either our ancestors stayed in the shade and had no access to the resources of the open landscape, or they found a way to cool down. The solution? Evaporation. The physics is simple. When water evaporates from the surface of skin, it carries heat away with it. 1 gram of sweat evaporating removes nearly 600 calories of heat. It's the most efficient cooling mechanism that exists in nature. But most mammals have a problem. Fur blocks evaporation. Sweat can't effectively evaporate from skin covered in a thick layer of hair. That's why dogs pant. They cool through the wet surface of their mouths, not through their skin. Humans took a different path. Somewhere between 2 million and 1.5 million years ago, several changes happened simultaneously. Body hair began thinning, and the number of eccrine sweat glands began rising sharply. Homo ergaster, the first human without fur. Homo ergaster, working man, lived in Africa roughly from 2 million to 1.5 million years ago. Skeletally, they look almost like a modern human. Long legs for running, narrow hips, tall stature, a body built for movement across open terrain. Genetic research allows us to roughly date the loss of fur. Alan Rogers, a scientist at the University of Utah, studied mutations in the MC1R gene, the gene that controls skin pigmentation. His conclusion? Dark skin pigmentation appeared in our ancestors approximately 1,200,000 years ago. And that matters enormously, because dark skin is only useful when skin is exposed. While fur covers it, ultraviolet light never reaches the pigment cells, and pigmentation is irrelevant, which means by the time dark pigment evolved, the fur was already gone. This is powerful indirect evidence. We can't find the last hairy ape or the first naked human. Soft tissue doesn't fossilize. But we can reconstruct the moment of fur loss through pigmentation genetics. It's like dating when a wall was painted by analyzing the color of the paint. Indirect, but reliable. Every population in sub-Saharan Africa today shares the same protective version of MC1R. That means it swept through the entire population, replacing other variants because it gave a survival advantage. Dark pigmentation became universal. And that happened approximately 1,200,000 years ago. By that point, the fur was already long gone. But here's a question that rarely gets asked. Why did fur start disappearing in the first place? Evolution doesn't have a plan. Nobody decided, let's get rid of the fur and replace it with sweat glands. Every mutation has to give an immediate advantage. Otherwise, it doesn't stick. The first to lose fur weren't adults, it was infants. This is a crucial observation. Newborn chimpanzees have significantly thinner hair coverage than adults. That's biologically normal because infants get warmth from their mothers and don't need their own insulation in the first few months. It's possible that the earliest mutations reducing hair were neutral or even beneficial specifically for infants. They overheated less during fever, cooled more efficiently. And then those same mutations spread to adults, and that's where they became seriously advantageous. Bare-skinned ancestors could run longer in the savanna, hunt more effectively, bring back more food. But there was another reason, one that gets far less attention: parasites. Dense fur is home to ticks, fleas, and lice. In the savanna, that kills you. Ectoparasites, ticks, fleas, lice, aren't just an annoyance. They're disease vectors. Malaria, Lyme disease, encephalitis, typhus, all transmitted through bites. For a densely furred animal that sleeps in one place and lives in a group, the parasite load can be overwhelming. Researchers found that as our ancestors began spending more time on the ground and in caves rather than in the forest canopy, parasite intensity increased dramatically. Bare skin solves this problem decisively. Parasites have nowhere to hide, attached ticks are immediately visible and removable, and the chances of mass infestation drop sharply. Mothers with less fur lost fewer offspring to parasite-borne diseases. That's direct natural selection. There's one more factor that often gets missed. When our ancestors began using caves and permanent camps instead of trees, the conditions for parasites became ideal. One place, the whole group, night after night. Fleas and bedbugs accumulate in a permanent den over months. This is what researchers call the sedentism curse, and it follows us today. It's why bedbugs live in mattresses, not in trees. You could argue we lost our fur partly because we learned to live indoors. And then there's a third hypothesis, the most unexpected one. Fur was lost because of mate choice. That sounds strange, but there's serious biological logic behind it. Biologist Mark Pagel of the University of Reading proposed the sexual selection hypothesis. The core idea? Bare skin is an honest signal of health. On a furry body, parasites are invisible. On bare skin, every tick, every louse, every blemish is in plain sight. If females choose males with the fewest parasites, they're choosing males with the strongest immune systems, which means that whoever had cleaner, barer skin gained a reproductive advantage. This is the same mechanism as a peacock's tail. A peacock's tail is inconvenient, energetically expensive, and makes the bird more visible to predators. But it proves I am healthy enough to afford this luxury. Bare skin sends the same costly signal. I'm clean. I have no parasites. I'm healthy. Most likely, all three pressures operated simultaneously. Thermal load demanded cooling. Parasites created selection for bare skin. Mate choice amplified the process. Three independent pressures, all pointing in the same direction. This is called multiple selection. When several independent factors push evolution in the same direction, change happens faster than any single pressure alone could manage. Interestingly, this triple pressure pattern explains why human fur loss went so much further than in other naked mammals. An elephant lost most of its fur because of body size and heat. A hippo because of water. One reason, one outcome. Humans had three overlapping pressures, which is precisely why the process went so far, all the way to the near complete disappearance of visible body hair. But then why did we keep hair on our heads? The head is the brain, and the brain is the organ most sensitive to overheating. During intense running under a blazing sun, the majority of radiant heat arrives from above. Hair on the head creates an air gap that prevents solar radiation from directly heating the skull. Calculations show dense head hair reduces the thermal load on the brain on a hot day by roughly 60% compared to a bare scalp. That's the answer. Fur left where it was a liability, the body. It stayed where it was needed, the head. The beard is more complicated. Biologist Mark Pagel considers it a sexual signal. It appears at puberty and recedes with falling testosterone, honestly advertising hormonal status. A 2020 study from the University of Utah found that a thick beard reduces the force of impacts to the lower jaw by around 30%, which may have mattered during conflicts. Most likely, both factors work together. Humans are the greatest long-distance runners on the planet. That's literally true. Not the fastest, not even close. A cheetah hits 70 miles per hour, a horse does 40. Even a dog beats a human in a sprint. But over long distances and hot conditions, humans are unbeatable. The traditional hunting method of peoples who have lived as hunter-gatherers into modern times is called persistence hunting. The hunter doesn't run fast, the hunter runs long. They pick an antelope, a kangaroo, or a deer and simply follow it. 1 hour, 2 hours, 3. The animal is forced to sprint repeatedly and eventually dies of heat stroke, because it has no cooling system like a human's. The Bushmen of the Kalahari, the Hadza of Tanzania, Aboriginal Australians, all practice this method. The hunter jogs steadily, keeping the animal in sight, never giving it a chance to rest. An antelope burns through its glycogen stores in a few minutes of hard running, then needs a pause to recover. The human doesn't allow that pause. The critical moment is midday. That's when the antelope, overheated from being pursued, stops and stands with its head hanging. Its cooling systems can no longer cope. The human simply walks up. Losing fur gave us access to meat. And meat changed everything. High-calorie food allowed us to fund the brain. The human brain consumes 20% of the body's total energy, an extraordinary amount. No other animal can afford that. But with access to a protein and fat-rich diet, we could. The brain began growing. And with brain growth came more sophisticated tools, language, and social coordination. The horse is the only large animal that comes close to humans in endurance. That's why in various cultures there have been competitions between humans and horses over long distances. In Wales, the man versus horse marathon, 35 kilometers, is run every year. In hot weather, humans win regularly. This works because humans cool continuously while moving. Sweat evaporates from bare skin even during running. A horse sweats too, but its skin is partly covered in coat, so cooling is less efficient. An antelope cools through breathing, meaning it has to stop to cool down. Humans don't need to stop. That's the decisive difference. Humans cool actively while moving across their entire body surface, 4 million glands working simultaneously. That's not just convenient, it's a fundamentally different biology of hunting. It also explains something else: why we carry so little subcutaneous fat compared to other primates of similar size. Fat is thermal insulation. It interferes with heat loss. Human fat stores are localized to the abdomen, buttocks, and thighs, not because it just happened that way, but because those are precisely the places where fat least interferes with thermoregulation. But how do you survive the night without fur? At night in the savanna, even in the tropics, temperatures drop to the low 60s Fahrenheit. For a bare body, that's cold. Fur would have helped. But the loss of fur and the growth of the brain turned out to be connected in one more way. Bare skin forced the invention of fire, clothing, and shelter, not as luxuries, as survival necessities. The earliest evidence of controlled fire use dates to approximately 1 million years ago. The earliest hide working tools from 100 to 150,000 years ago. These weren't random inventions. They were answers to a specific biological problem. A body without fur gets cold at night. The need for fire accelerated cultural development. The need for clothing demanded planning, hide processing, skill transmission, in other words, language and social learning. Losing fur triggered a technological revolution. And there's a way to verify this through biology. Scientists studied the genome of the body louse, Pediculus humanus corporus, and compared it with the genome of the head louse. Body lice live only in clothing. Their ancestors migrated from human skin to clothing exactly when clothing appeared. Analysis of the genetic divergence between the two louse species showed this happened approximately 80 to 120,000 years ago. That's independent confirmation. Clothing didn't appear 10,000 years ago with agriculture. It appeared 100,000 years ago as a direct response to cold nights without fur. Lice turn out to be unlikely but precise historians of our evolution. You still have fur, you just can't see it. Technically, an adult human body has roughly the same number of hair follicles as a chimpanzee. The difference is that in humans, most of those follicles produce thin, nearly invisible hairs, vellus hair. They're present almost everywhere, on the forehead, arms, and back. That tells us something important. We didn't lose the hair-producing system itself, we reprogrammed it, from thick, protective fur into barely visible fuzz that barely interferes with heat loss, but actually increases the tactile sensitivity of the skin. This was fine-tuning, not a reset. Why humans come in different skin colors. It's the same story. When fur disappeared, skin found itself directly under ultraviolet radiation. UV destroys folate, a vitamin critical for fetal development. A pregnant woman with low folate levels risks giving birth to children with neural tube defects. Dark skin, high melanin content, protects folate from UV destruction. So the first bare-skinned humans in Africa rapidly became very dark-skinned. But when part of the population began migrating north, where sunlight is weaker, the opposite problem emerged. Dark skin blocks vitamin D synthesis as well. Vitamin D deficiency causes rickets, weak bones, and immune problems. In northern latitudes, lighter skin was an advantage. Different skin colors are not different biological types. They're one and the same adaptation to solar radiation, just calibrated differently at different latitudes. Why didn't other primates go the same route? Chimpanzees are our closest relative. Our lineages split roughly 6 to 7 million years ago. They too faced changing climates. But chimpanzees kept their fur, because chimpanzees never left the forest. They stayed in the shade, where, at moderate activity levels, heat stress simply isn't a problem. Their survival strategy was different. And it worked, too. This is a reminder. In evolution, there is no single correct path. Fur is a perfectly functional solution for the forest. Bare skin with sweat glands is a perfectly functional solution for open terrain in the heat. Better means better in a specific context. Climate data from the past several million years shows Africa was getting drier and cooler. Forests were giving way to savanna and grassland, And during that same period, most species of Australopithecines, our evolutionary cousins, went extinct. Some tried to stay in the forest as the forest disappeared. Others moved into the savanna and couldn't adapt. The ones who survived were those whose biology happened to be flexible in exactly the right direction. Losing fur wasn't a loss, it was a trade. We gave up passive protection and gained an active cooling system, gave up insulation and gained tactile sensitivity, gave up parasite concealment and gained parasite visibility, gave up warmth at night and gained the motivation to invent fire. Every loss pulled a new solution in behind it, and every new solution opened the next door. That's evolution working at its best, not by eliminating the problem, but by building a creature that knows how to deal with it. Every time you feel hot, you're using what saved our species. We live in a world where most of our time is spent in temperature controlled spaces. We dress for the weather, we run the heating in winter and the air conditioning in summer. Sweat glands are barely needed in an office, but they haven't gone anywhere. Under stress, during exercise, during fever, the same system kicks in. The same 2 to 4 million glands that saved our ancestors from heat stroke on the savanna are working right now. Drops of sweat on skin aren't an inconvenience. They're one of the most important biological innovations in the last several million years. They're what allowed a small, hairless creature to step out of the forest shade, cross a scorching savanna, and eventually populate every continent on the planet. Evolution didn't think, didn't plan, had no idea how this would end. One day, one hair follicle simply produced a slightly thinner strand than usual. Its bearer survived, left offspring, passed it on. 3 million years later, that creature is standing here telling you this story.